Hello everybody, and welcome back to another Eng 130 video tutorial. In this tutorial we're going to cover the first friction final exam example, and this comes from the 2013 midterm. So again, this was my midterm. I did not like it. Not midterm. I warned you guys in the last video I'm going to say midterm a lot. I meant final. Again, this was my final, and this is the question that kept me up at night long after the final. It was like a nice Christmas present from all the professors. And the present was no sleep during the break. So hopefully they're not too mean on you guys this year. But yeah, no, this one really sucked because this was more of an algebra question than anything else. But we're going to get started, and hopefully you guys can take away a little bit of friction from this. The concepts of friction in this one are actually very simple. The only thing, there's maybe I'd say one good trick in it, and I'll show you guys the trick. But after that, this is, again, I feel it's more of an algebra question. So this one got kind of messy, but then got nice at the end. So I'm hoping that I can solve this video, and I'll never have to show anybody how to do this again, because I hate it every year when students come to me asking me how to solve this one, because, again, this brings back terrible memories, just terrible memories. But let's get started, hopefully for the last time. So looking at the example, it says, concrete pipe A rests on top of concrete pipe B and C. And we kind of see that in the figure. All pipes have the same radius R and weight W. The angles between the center of the pipes are defined by angle theta. So this one's kind of important, but you can kind of see it. And the coefficient of static friction between the pipes is U. So anything between the pipes is U. And between the pipes and the ground is U prime. So we're just going to kind of show this right here. So at this point of contact right here, this is of course going to be U. At this point of contact over here, we're going to have U as well. But then below the pipes, between the pipes and the ground, these ones are going to be U prime. So U prime. All right, continuing on. And this is where... This is where things start to suck. It says determine the minimum values of U and U prime in terms of theta so that the pipes will not slip. So we need U and U prime only in terms of theta. And that in terms of theta really, really sucks. So that means that it can't have any friction in it, any normal force, any weight. Our final answer should be just in terms of theta. And then the last part, which is kind of obvious because for friction questions, you're definitely going to have to do this. Ensure that you draw the appropriate free body diagrams. So whenever you're dealing with friction, any friction situation, you're going to have to draw a free body diagram. That should be kind of given to you. So hopefully you guys understand that, yes, I will need a free body diagram for this question. But now here's kind of the hard part of friction when you have multiple bodies. It's where do I start? Because in this question, there's actually 6 free body diagrams that you guys can draw. Actually, even more. You can draw lots more, but every time you have things connected by friction or friction created between a surface, you don't necessarily have to split it up. And I'm going to show that right now with my first free body diagram. So my first free body diagram I'm going to draw, I'm going to go 1. I'm going to put all 3 pipes. So my free body diagram... And this one's going to be all 3 pipes. Now you're saying, okay, Clayton, you just said all 3 pipes. What do you mean all 3 pipes? I mean, I'm going to draw a free body diagram with all 3 of the pipes still together. So what I'm going to do is I'm going to come down here and I'm just going to draw 1 circle and then I'm going to copy it. So I got a circle. So this will be my first pipe. So I'll put this down, let's say over here, and I'm going to copy it. I'm going to paste it twice. So I don't know what just happened. Oh, I came up here. So I'm going to undo that because I want to paste it down here. Perfect. So I got my second pipe up here. I'm going to paste it. And hopefully I can throw it over here. Huh. I didn't expect it to take the background with it. Can I bring this one to the front? Alright, delete this one. Let's go back to this one. Copy and paste. So hopefully this is not going to work. Oh my god, it's just getting worse. All right, I'm just going to draw them because, yeah, this is getting a little bit messy. So going back to the marker, I'm just going to draw the other pipe, and we see that the other pipe, I don't know, let's say it's somewhere there. So what I did is I just drew all three of the pipes, but notice that I didn't put any friction between the pipes, and that's because I didn't separate them. Only when you separate things do you draw the forces between them. It's kind of like a truss. If you don't cut a member, you don't want to draw any of the forces between them. However, I did separate the bottom of these pipes from the ground. So there's going to be forces on these pipes from the ground. So the first force, which is always kind of, everyone will know, is we're going to have a normal force. So between the ground and the pipe, there's going to be a normal force holding these pipes up. And it makes sense. These pipes aren't just going to fall through the floor. There's going to be a normal force. And it says that anything between the pipes and the ground is prime. So what we're going to do is this is going to be N prime, and we have N prime. In addition to the normal force for vertical loads is we know that each one of these pipes has a weight. And the weight acts directly at the center. And it says that all three pipes have the same weight. So I'm going to draw 3 arrows. And each one of these is going to be at the center of the pipes coming downwards like this. So we got 3 arrows, and each one has the same weight, which is W. And now we have to draw friction forces, because of course whenever we have that normal force, there's going to be a frictional force. So at the bottom of these 2 pipes, there's going to be a frictional force. But now we have to figure out, okay, what's the direction of these frictional forces going to be? We don't know if it's going to go to the left or to the right. And this is where we're going to have to kind of use our intuition and think about, how does this system work? How does this system move? So if we have a pipe at the top, so the whole kind of thing that's going to happen is, you guys kind of visualize this. If the weight of the pipe at the top is too heavy, or the angle is too big, something like that, what we'll find is this pipe in the center will want to come downwards, like this. It makes sense. You guys can kind of visualize that the pipe wants to fall down. And what's going to happen is if that comes downwards, it's going to push these 2 pipes out to the side, like this. And if that's the case, and this is the direction of motion, we know that our frictional force, of course, is going to want to resist it. So our frictional force, in this case, is going to be coming inwards. And this is F prime. F prime. So this is the frictional force trying to stop those pipes from separating and falling apart. So I'm just going to erase the direction of motion real quick. And then, of course, with 3-body diagrams, we got kind of 3 scenarios that we can do. We can take, sorry, not 3 scenarios, 3 equations of equilibrium. So if we look here and we go sum of the forces in X, well, not going to get too far. What we're going to find out is that F prime is equal to F prime. Well, no shit. So we take a moment. Well, we don't know any distances. So taking a moment's also not going to really do too much for us either. So one thing that we can do, however, is we go sum of the forces in Y is equal to 0. What we find is we have 2 normal forces, N primes, going upwards. So we got 2 N prime going upwards. And then we got 3 weights coming downwards. So minus 3W is all equal to 0. So what I can do is I could rearrange this equation and go, therefore, N prime is going to be equal to 3 over 2 times W. So this doesn't exactly give me any parameters, but it gives me kind of a start. So because I'm going to call this one right here equation 1. And whenever you see me, and you guys probably know this from before the midterm, whenever you see me go equation 1, you know things are going to become real dumpster fire real fast. So that usually means that we're going to have to start solving systems of equations, and in this case we will. And the thing that really sucks about this one is when we had system of equations before, I would tell you guys, throw in your calculator, throw in your calculator. Well, for this one, not so simple, because everything is parametric. We're not working with numbers, so kind of difficult to do that. But looking at this 3-body diagram, well, we're done. Again, we can't do sum of the forces in X. It'll just give us F prime equals F prime. When it comes to moments, well, we don't know distances, so we can't do any moments. So right now, we're stuck with one equation, and that's N prime is equal to 3 over 2 times the weight. So what we do, we move on to another free body diagram. So I'm going to go free body diagram. And for this one, what I'm going to do is I'm going to do a single pipe. So I got kind of two choices. I got pipe A, or I got pipes B and C. And the reason why I say B and C as a single choice is because they're in the exact same position. So the free body diagrams are actually going to be identical, just kind of on opposite sides. So it leaves me between, let's say, pipe A or pipe B. And if I look at A, well, I'm going to have a lot of things in terms of just U, but nothing in terms of U prime. So maybe A is not the best to start with because I won't have any relationships between U or U prime or anything like that, because in the end I want to solve for something that has U prime in it, and I can't do that with free body diagram A. So what I'm going to do is I'm going to start with free body diagram B, and if I need to later on, well then I can go to A. But for now I'm going to go and just draw pipe B. So I'm going to go pipe B. Alright, so what I'm going to do is I'm just going to draw, and I'll draw this one a little bit bigger. So we got our pipe. Put it right here. At the bottom, well, we already kind of drew it from the other picture because it's in this bottom. We know that we have a frictional force going to the right. And this one is F prime. We know that we have a normal force holding this pipe onto the ground, like this, which we know is N prime. And we know that this also, of course, has a weight coming downwards, which is W. So this is between the pipe and the ground, and then, of course, the weight. So nothing new, because we had this all before. But now, since we split this pipe away from the other pipes, we have to include the frictional forces between pipes A and B. So up in this corner over here. So what I'm going to do is I'm going to draw kind of the little dotted line that they drew too, like this. And we know along this dotted line we have a normal force. So of course there's going to be a oops, I want to make this kind of go perfectly along here, and it kind of, I think, auto corrects it, but I don't want to auto correct it, so we'll just say like this. So we know there's going to be a normal force on here from the other pipe. And this normal force, since it's between the pipes, is just N. They said up here that they want anything between from pipe to pipe just to be U, so we're just going to call this normal force N. And we know that because of the normal force, there's also going to be a frictional force between the two pipes. So we know there's going to be a frictional force here, but we don't know exactly which way it acts yet. So right now I want you guys to kind of think. I'm going to show you guys the situation of the pipes. And I want you guys to think real quick, because this is the hardest part of friction, is figuring out where the hell do things go. And for this one, it's actually a little bit tricky. So I want you to look at the situation real quick, take a good gander, maybe pause the video. Alright, and then we're going to come down here. I'm going to ask you guys, do you guys think it's going to go to kind of go upwards and to the left, or downwards and to the right? And you guys just said your answer. You guys are probably talking to yourself in Lister, which is always cool. Well, the correct answer is this is actually going to go downwards and to the right, like this. And this is going to be F. And then a lot of you guys are thinking, wait, what the hell, Clayton? No way. Because if we look at the equations, sorry, not the equations, the motion for these pipes, again, we said A goes down like this. So these pipes want to separate. Like this. So these pipes want to move this way. So shouldn't the friction try to kind of counteract that? So looking at pipe B over here, if it's moving to the left, shouldn't the friction try and resist it a bit? Well, no, the answer is not. And the best way to find the answer for this one, which I always found kind of difficult, is we have to look at pipe A real quick. So if I were to draw pipe A, oops, the pipe A after it's been crushed by something. So this was pipe A. We know pipe A is coming downwards. We know pipe A wants to come down like this. So therefore the friction on pipe A wants to resist the movement like this. So this friction on pipe B, well, it's hard to figure out. That's why we have to kind of think about pipe A. Because if we know the friction on pipe A is going up, then the friction on pipe B is going to be the opposite. So this is why the friction here is going to go downwards, like so. So that's kind of why, but we're going to move on. So now if we look at this, we have 5 unknowns. We got 2 F's, 2 N's, and then we have a W. And of course we should always label distances if we have them, so we know that the radius of this pipe is going to be R. So this is going to be distance R. And then we should also label the fact that this force acts at an angle theta. And this theta is going to be very important because this theta is what we need our final answer in terms of. Remember, if we look up at the question, it says we want our final answer in terms of theta. So we're going to have to use that one quite a bit. So same process as before. I'm going to go through some equilibrium and try and figure out some equations to hopefully solve for things. So I'm just going to start with the one normally, sum of the forces in x, that's equal to 0. So looking at this, well, we got f prime heading to the right, so we're going to have f prime. And we got regular f also heading to the right, so we're going to go plus f. But we have to realize that just a component of f is going to the right. So it's going to be f times cosine of theta, like this. And if we look, we have n going to the left. So we're going to have minus n, and this one's going to be times sine of theta. And we know equilibrium, everything must be equal to 0. And as the fun continues, we say this is going to be equation 2. So we can just move on, keep going down. We could go sum of the forces now, and y is equal to 0. So we do that and look up here. Well, we got n prime coming up, but then we got the weight coming downwards. So n prime minus w. And we have the frictional force going downwards, so that regular f, so minus f times the sine of theta. And we also have that normal force n also coming downwards. So we're going to go minus n times cosine of theta. And equilibrium, everything is equal to 0. I got another equation, so let's label this one equation 3. And finally, and this is kind of a special thing for cylinders, is we can always take a moment. So for friction, I've only ever seen moments used for 2 scenarios. One is when crates are tipping, and the other is finding the friction on a wheel. Because if we do this, so some of the moments, and I go at O. So this basically means at the center of the wheel, so I'll just put an O there. The sum of the moments at the center of the wheel must equal 0. And if we look at this, the only thing that's creating moments, because everything actually the center, is the frictional forces F. So from here, we see that F prime times the radius R minus F times the radius R is equal to 0. So I'm not going to say that this is equation 4, because from this we can actually directly manipulate it, and we can move F and R to the other side and then divide by R. What we get is F prime is equal to F. And this is very, very common for wheels that have 2 points of contact. Our F prime, or basically the friction at one point, is going to be equal to the friction at the other point. And now I'm going to call this equation 4. Well, it's kind of an equation, but it's more just kind of a nice fact. F prime is equal to F. So at this point, what we basically have is 4 equations, and we can just try and start manipulating them to hopefully make something work. So what I want to do is I want to try and make things, of course, as easy as possible for everything. So what I'm going to do is I'm going to say, okay, I have 2 major equations, and those are 2 and 3. Equation 4 and equation 1 up here, well, those are just kind of simple, nice little tricks. So what I want to try and do is put those 2 equations into my major ones, which are 2 and 3, to try and figure out some more relationships. So what I'm going to do is I'm going to sub, and these are my 2 relationships, 1 and 4 into, so I want to put these into my major equations, which are going to be 2 and 3. So I'm going to come down here and I'm going to look at equation 2. Well, the first thing I have there is f prime. So f prime is between the ground and the wheel. So I can go with f prime or I can switch it to f. It doesn't really make a difference. So what I'm going to do is I'm going to say, okay, let's keep this as f prime. And now we're going to go f prime. So we're going to keep this as f prime. And if we look at the next thing in equation 2, it's plus f. So instead of f, we know that f is equal to f prime. So I'm going to turn the f into f prime. And then times cosine of theta. And then minus n times the sine of theta. Actually, we know that n now is equal to, oh sorry, n prime. I just really got tricked. See, you got to pay close attention. N times sine of theta is equal to 0. So the only thing I really switched in this equation is the f to f prime in the cosine of theta. So I'm going to call this now equation 5. And I'm going to do the same thing to equation 3. So we had n prime, but if we look up here, we know n prime is actually 3 over 2 times w. So I'm going to have 3 over 2 times w. And kind of moving forward after that, we got minus w minus f. So minus, and we're going to switch the f to f prime times sine of theta minus n times cosine of theta. And all this is equal to 0. So we're going to call this one now equation 6. So now we got two equations that we took advantage of all our relationships. And now what we can see is, okay, we can take something of equation 5 and throw it into equation 6. So the thing that jumps out to me, because I can rearrange 5, so I'm just going to go rearrange 5, because 5 actually has some really nice stuff in it. Rearrange 5. So that's the top equation of the two. And we got f prime plus f prime cosine of theta. And if you guys know this from math, we can actually factor out an f prime. So we're going to have f prime, and then in brackets, we're going to have 1 plus cosine of theta. And then we have minus n times sine theta. Well, what I want to do is I'm going to move that to the other side. So this is equal to n. But I want n just kind of by itself. So what I'm going to do is divide both sides by sine theta. So the sine theta on the other side is going to kind of go away. Oops, and this didn't work. So I'm going to put a sine theta on the bottom of this side. Because now I have a nice equation for n. And I'm going to call this right here number 7. So I'm going to take this nice thing I have, number 7, and I'm going to throw this into equation 6 and see what I get. So coming down here, what I have for equation 6, well, the first thing I have is 3 over 2w minus w. Well, that's basically 1.5 minus 1. So what we have on this side is actually just w over 2. So this doesn't come from the substitution. This is just making things a little bit easier. And then we have minus f prime sine theta and then we have minus n. So instead of n, I'm going to put my f out. So I'm going to have f and bracket 1 plus cosine of theta and sorry, this is f prime, and then this is divided by sine of theta. So this is when I'm substituting my nice relationship from equation 7 into equation 6. And then we know that n up top in equation 6 is multiplied by cosine theta. So we have to add a cosine theta at the end. And of course, this is all equal to 0. Excuse me. So what I'm going to do now is I'm going to move the f's to the other side, because I see I got a lot of minus f, and on the one side I got w over 2, which is already nice and positive. So coming down here, I'm not going to write equation 8 because I'm just going to keep rearranging this. I'm going to get w over 2 is equal to, so I'm going to move f times f prime sine theta, to the other side. I'm also going to move the f prime 1 plus cosine theta divided by sine theta. But what I'm going to do, hopefully to find a relationship, is I'm going to take this cosine theta at the end here, and I'm going to multiply it in to give me kind of two separate terms. So I'm going to multiply this in like this. So the first one I'm going to have is f prime, so plus f prime, and then times cosine of theta, because cosine of theta times 1 is just cosine of theta, divided by sine theta. And then plus f prime, and then we have cosine theta times cosine theta, so we're going to have cosine squared of theta divided by sine theta. All right, so now we have to try and find more relationships. And the one thing that always jumps out to me when I do trig is I always think, I hate it when I have something in the denominator. And right now, 2 of the terms have sine theta. So I ask myself, okay, how the hell do I get rid of those? And I know I can multiply everything. And that's kind of the trick, everything. A lot of students will just multiply one side. Well, that won't work. We need to multiply everything. So multiply both sides by sine theta, because this will cancel out sine theta on those two end terms, which is very nice. It would be nice to get rid of them. So the trick is, remember, we have to make sure that we do it on both sides. So we're going to have w over 2, and then this is times sine theta now. It's going to be equal to, and then f prime sine theta times sine theta, well, that's going to be f prime sine squared of theta. And then we're going to have f prime cosine of theta, but since we multiply by sine theta, the sine theta on the bottom cancels, so this is going to be plus f prime cosine of theta. And then multiplying by sine theta will also cancel the sine theta on the denominator of the last term. So it's going to be plus f prime cosine squared of theta, but nothing on the bottom anymore. Perfect. So we're finally starting to get somewhere. And the next thing I notice looking at the right hand side is I have f prime in every single one of those terms. So what I'm going to do is factor out f prime, and I'll write the step down so you guys know exactly what I'm doing. Factor out f prime. So if I do that, I'm going to get w over 2 times sine theta is equal to f prime, bracket, I'm going to have sine squared of theta, and then I'm going to have plus cosine of theta, but what I'm going to do, because it's actually a nice trig relationship, so I'm going to go plus, and I'm going to put the last term in next, which is the cosine squared theta. And then I'll add the cosine theta from the middle term. So I just factored all this out. And what you guys will see, looking at here, is we all know that sine squared of theta plus a cosine squared of theta, well, that's just going to be equal to 1. So from this equation now, we're going to have w over 2 times sine of theta is going to be equal to f prime, and then in brackets we're going to have 1 plus cosine of theta. So this looks a lot better now. So you see how things get really messy, but they always kind of work out at the end. So what I can do to finish this off is I can just move the 1 plus cosine theta to the other side to give us a nice kind of equation for f. So we can say that f prime, which we know from equation 4 is also equal to just f, is going to be w sine theta divided by 2, and then in brackets, 1 plus cosine of theta. So, got a nice relationship right here, but we're still not done. Although we found a nice relationship, it's not asking for what the friction is equal to. It's asking for what is the minimum mu and mu prime so that these pipes don't slip. So coming down here, now that we got nice relationships for f prime and we got 1 for n and we got 1 for n prime at the top here, we have to ask ourselves, okay, well, when will we use mu? And the question says this: what's the minimum one for it not to slip? So if things are just about to slip, so if they're on the verge of slipping, we know that f is going to be equal to mu times n. And the same thing is going to go for the other surface. We know that f prime is going to be equal to mu prime times n prime. And this is when it's just about to slip. Just about to slip, it's equal to. If not, it has to be less than. So the minimum value of mu is going to come when these two are equal to each other. F is equal to mu times n. The second it gets anything smaller, the second it changes, well, then we got a big problem. A really big problem. So the second mu gets any bigger, when it gets any smaller, we have a problem because our friction force exceeds that and things are going to start slipping. So what we're going to do is we're going to rearrange both of these equations. And we're going to say that we can find out that mu is equal to f over n. And we know that mu prime is equal to f prime over n prime. So assuming that we know what f prime, n, and n prime are, we can actually solve everything that we need to do. So let's do the first one real quick. We know that mu is equal to f divided by n. So now we got to kind of figure out, okay, well, what are all our relationships that we used? And if we look up here, well, we found something, and I'll call this equation 8 now, I guess. We found equation 8, which is f. And if we look up here, equation 7 is n. So when we put these in, we know that we can put n at the bottom. So if we look up at n, we see that n is equal to f prime times 1 plus cosine of theta divided by sine theta. So this is n at the bottom. And if we look, we also know that f is actually just equal to f prime. So I can put this here, and when we check, we can go, okay, well, this f prime at the top is going to cancel with the f prime right there. So our final answer for mu, so mu is going to be equal to sine of theta divided by 1 plus cosine of theta. So as you guys see, the final answer is actually not bad at all. It's kind of messy, but you guys can solve it. Again, this is not one I would want on final, but it's not as bad as it looks. But when you're in a final, everything looks bad. That trust question, that first question looks bad when you're in the middle of a final. So that's mu. But remember, our goal isn't just to find mu, it's also to find mu prime. So we're going to come down here and say, okay, well, mu prime is going to be equal to f prime divided by n prime. So we come down here and we say, okay, well, if we look up at what f prime is, we know f prime is w sine theta. So I'm going to put this up here. So this is going to be equal to W sine of theta. And then we look down here a bit. Divided by 2 plus 1 plus cosine theta. 2 times 1 plus cosine of theta. So this right here, this is just the f prime. It's a lot of work for just f prime. What I should do to kind of show you guys too is I'll put extra brackets around it. And we have to divide it by n prime. And n prime we know is actually just 3 over 2 times w. And where did we get that from? Well, that was actually the very first equation we did at the top. Right here, n prime is equal to 3 over 2 times w. Equation 1 we called it. So we come down here. Well, we can actually see that a lot of things, well, not a lot of things, but some things cancel. Like the w here and the w here, along with the 2 here and the 2 here. So in the end, what we see is that mu prime is actually equal to sine of theta divided by 3 times 1 plus cosine of theta. So it's actually the same answer. The only difference is the bottom is multiplied by 3. And that's it. So we're going to box this answer, 2, and we're going to, oops, I keep messing this one up at the end. All right, let's try again. Box this answer as well, and this is it. So these right here are the two answers. We have mu and mu prime, and both are just in terms of theta. So that's it for this question. Again, it's a very challenging question, especially the fact that it's parametric. No one wants to do anything parametric, so that just kind of adds to the pain of it, but it is doable. Even though this question for me at the time was not doable, it was very impossible. But I can do it now, I guess. So just think, even if you can't solve your final this year, you'll look back in 6-7 years and say, oh, that wasn't too bad. Well, at least hopefully. Alrighty, so I think that concludes this friction question. Again, as you guys saw, the friction was very basic. It was more just a lot of algebra, trig, all the boring stuff really. So yeah, hope you enjoyed this. I hope this helped you guys, and thank you guys all for listening. I'll see you guys in the next video.